So, time for our next talk, and we're excited to have Erik Petersen from Duke University here. He's making a little bit of a sacrifice coming over here to give a talk on this particular Saturday, because I know in the Duke universe that this is a big day, but that's later today, right? Yeah. Okay. So thanks for coming down here. He's part of a vibrant cosmology group at Duke University, and they've got a lot going on down there. And so we reached out to them and said, "Hey, can you send us somebody for TriStar?" And they said, "We know just the guy." And so here he is. He's originally from Seattle area. He went to Notre Dame as an undergrad. So Steve Desch, our other astronomer here, is a Notre Dame grad. And now he's at Duke, where he's interested in figuring out how Type 1 supernovae, you can make some refinements on how you make those observations to refine the cosmological parameters that allow you to understand the universe. So he's going to tell us about his research. Erik?
Hello, everybody. Hello. Can people hear me back there? Oh, great. So yes, Tom introduced me well. I'm Erik Petersen. I am a fourth-year PhD student at Duke University studying supernova cosmology. I study exploding stars to better measure the expansion of the universe. So today, the premise that I want to go with is, so I've taken an image with a telescope. Now, how do I measure the expansion of the universe? And I reflected on the title a little bit more, and I decided, no, I want to change the title just a little bit, and I hope this is okay with Tom. I want to change it to this. So you've taken an image with a telescope. How do you measure the expansion of the universe? So I know that there are experienced astronomers in this room, many of them, but I want to go back to the basics. I want to make sure that every single person in here feels comfortable by the end of this talk in measuring the expansion of the universe yourselves. So let's see how that goes. I promise that we will go to the basics, but I have to start with this image, and maybe you're saying, "Erik, this looks pretty complicated to me." But this is an interpretation of how the universe was formed and has formed in the last 14 billion years. We start here in the Big Bang, and we enter into this inflationary period where the universe expanded extremely quickly, super fast into a really big universe really, really quickly. And it has expanded since then as we've developed the first stars, developed the first galaxies, the first planets, etc., until we get to today. And what you notice here, and I won't get to talk about it too much today, but you'll notice this uptick in this diagram here. You kind of notice that here's a little bit of a slow but constant increase or expansion of the universe, and we notice this uptick here. This is due to dark energy. And dark energy is what causes the accelerated expansion of our universe, and something that was discovered only in 1998, and the Nobel Prize was given in 2011 for this work. I won't get to talk about dark energy too much, but I had to mention that for sure in this talk. What I do want to talk about is how do we measure the expansion of the universe. So some of you may not know what that actually means. What does it mean that the universe is expanding? And here I have a little bit of an analogy, it is an analogy, using a blueberry muffin and its batter. So you imagine here, we're in the Milky Way, and we're in this blueberry. We say that this is a galaxy. And we have other galaxies in this blueberry muffin batter. And say this is early on in the universe, right? You notice that you're somewhat close to these other galaxies. If you let the universe bake for, say, 15 minutes, but really for billions and billions of years, you can tell that after some time, the universe has expanded. And what you notice is that not only are you further away from your other blueberries, you notice that the blueberries that were further from you, they're expanding faster and faster away from you. So the nearby blueberries, yeah, they're moving away from you, but not super quickly. You notice that the blueberries, maybe at the bottom of this muffin, have been moving away from you faster and faster. So that is describing to you the expansion of the universe. Now the question is, how do we actually measure this expansion of the universe? And my question I want to answer right now is, what do we need to measure the expansion of the universe? And I want to have all of you think for maybe 30 or so seconds, how do you measure the expansion of the universe? What is that? We understand what it means, what the expansion of the universe means now, but how do you measure that? So think for 10 seconds maybe. So I'll tell you, and I think I've boiled this down somewhat simply, I think that we need two things. Okay, we need two things. Number one, I think we need distances. So if we can measure distances to these galaxies, which are extremely far away, I think that can help us. That's a first step. I think we also need velocities. So if we're able to figure out the distances to some of the most distant galaxies in this universe, and we're able to figure out how quickly they're moving away from us, I think we can measure the expansion of the universe. We can characterize the expansion of the universe. And what I'll get into today, so we need these two things, distances and velocities, and I think that we need three total tools, three cosmological tools to be able to measure the expansion of the universe. And I'll get into those. So I've set the stage. We measure an image, or we take an image with a telescope, and we want to measure the expansion of the universe. Now I want to walk you through a story about how we do that. Okay? So first, what you do, right, is you got to take your image with your telescope. And you do that, you drive to a really remote location, you drive up to the top of a mountain, and you go find your scientific telescope, right? So this is me here in, I got to go to Chile. I got to go on an observing run here. Chile is one of the best places in the world to observe. It has high altitude mountains, and they're extremely dry. Anne told us that the weather is definitely a factor, and the weather at these locations is almost always good. So you drive up to the top of a mountain to your scientific telescope, and then you got to check out how's it look inside the telescope. All right, this telescope looks pretty good, right? Yeah. Well, the one thing you really do actually have to check for, make sure the ladder is not in the way. For when your telescope spins around, you don't want it to hit the ladder. Okay, so this was a little bit of a rude awakening for me. I think I knew this at the time, but maybe a little bit before this. I had this image of what it's like to be an astronomer. You get to go to South Africa. You get to look through your telescope at these beautiful objects or something, right? I found out, maybe not right before I did this trip, but somewhat before, that my conception of being able to look through these telescopes and see the most beautiful sights, that's not really how it is. And I was a little bit bummed, but I still thought this is pretty cool. So what happens is you use these instruments, these very sensitive instruments, to concentrate the light. So this is a reflecting telescope. You got your mirrors down here. You got a mirror up here, just like some of the small ones that maybe, I don't know, you've used sometimes. But these are massive mirrors. You concentrate the light onto a detector, onto a camera. And it was a little bit different than I expected, but I still think it's incredibly cool. So you go to the top of your mountain, you check out, you make sure that the telescope is looking all right. What's next? This is more what it looks like to be on an observing run. So this was on an observing run. This is one of my colleagues that I did in Hawaii. Hawaii is another great location for telescopes, the tops of those mountains. So you check out your telescope, and then you go into an observing room, actually. So this observing room is more than an hour and a half drive away from the telescope itself. And so you go into this room, and what you're doing on an observing run is you're monitoring every single thing that can be monitored. I told you these telescopes are incredibly sensitive. They're incredibly expensive as well. You need to take care of it. They cannot get rained on. They cannot freeze. You just have to take such good care of them. And so we're a little bit obsessed with monitoring, hey, are there any clouds? Or is there any bad weather coming in? We monitor, here's another image, checking if there are clouds coming in. And then you check for humidity levels. You're just looking and monitoring every single thing. You're looking for earthquakes that are happening. You need to protect your telescope. A few of these other monitors here, these are the telescope controls to actually manually move it around. We're tracking a star here in this image. And then you're getting just tons and tons of data. You're not actually getting to peer through the telescope, unfortunately. So we've got it all set. You go to the mountain, you check your telescope, you go to your observing room, you're ready to go. And I wanted to draw your attention to this monitor right here. I thought it was one of the most beautiful views. Not actually getting to look through at the galaxies, maybe what you might imagine. But I thought this was a super cool image. Looking in all different directions, I thought the colors were beautiful here. You can see the bottom half of Orion here with Orion's belt and the legs of Orion. And then you're also looking at, you can see a thermal camera here to make sure that there are no people or animals or something climbing on top of the telescope. Funny enough, that the night that I was on the observing here, this was last January, you can see 2022, last January, a neighboring telescope at the top of Mauna Kea reported that there were indeed people climbing on their telescope in the middle of the night, and so they had to call security on them. So that's a good camera to have. Okay, so you're ready to go. The sun is setting. You're excited to take your images, right? This is again me in Chile over here. The sun's setting, super excited to stay up all night, right? So this is my telescope that my thesis project will be using. This is called UCURT. I'll get to that later in this talk. But this one is in Hawaii. So you're ready to take your images, right? And this is what it looks like, right? No, that's not what it looks like. I had a little bit of a rude awakening. I kind of thought it was going to look like this, but I figured out it looks a little different. And you saw some images from Anne's talk, a little more what it looks like, right? Looks a little more like this, right? But I hope that by the end of this talk, you all can see some of the beauty in this image itself. So when we think about the premise of this talk, so I've taken an image with a telescope. How do I measure the expansion of the universe? I want you to think about an image like this. And the image is, you can see, a little pixelated. It literally is in pixels. We count light in pixels. And the reason why it doesn't look like this, and these are incredible images, we're trying to push the limits of our instruments, right? We're looking as far and as deep as we possibly can. And so this is, in some senses, the best that we can do. But we're able to measure the expansion of the universe with this. So how do we do that? I told you, we're going to look at distances and we're going to look at velocities. But first, those distances. And I think that we need two cosmological tools to be able to figure out these distances. Now, I had you think originally, how do you measure the expansion of the universe? And maybe some of you knew, maybe some of you had your own ideas. And maybe right now when I ask, we got to measure these distances, maybe you're thinking to yourself, that shouldn't be that hard. We're pretty good at measuring distances, right? I'll tell you, there's a big problem, and again, Anne told us about this. The universe, or distances between astronomical objects, are absurdly large. And we were talking about our solar system right here, which is incredibly large, and now we get to talk about the size of the universe. The universe. So here's your situation. You observe your distant galaxy here, and the light that you receive has a given wavelength, and it travels across space and time for millions and millions of years and lands on your telescope. So this may not come to you as a surprise. This may not come as a surprise to you, but this galaxy is not to scale. It looks a little more like that, and even that is not to scale, right? You could still see the dot that it points to, not even close to scale. These galaxies are absurdly far away. And so I promised we're going to go back to the basics here. I want to talk to you about how large the universe is. And to this day, it doesn't make any sense to me, even though we're going to step through each step. So light has a finite speed. It takes time for light to travel. And maybe you've heard the term of a light year, right? But I want to make sure we all know in here what it actually means. And so light has a finite speed, and that means that it takes time for light to travel distances. So I calculated out that from here to Los Angeles, that's about 2,500 miles, I think, if I'm remembering that part correctly. But it takes light 0.013 seconds for light to travel from here to Los Angeles. Okay? That's pretty quick. Light is extremely fast, right? But as you'll see, it takes longer and longer for light to travel across our universe. To take that next first step, the moon. That's 1.3 light seconds away, 100 times further than it is to Los Angeles from here, if I've done my calculation correct. It takes light 1.3 seconds to travel from the moon to us, and vice versa. Take it a step further. 8.3 light minutes away is the sun. So when you're staring at the sun during lunch, don't look at it directly. It takes 8.3 minutes for that light to travel from there to us. And it's just, it gets weird to me that when I'm looking at the sun, that light was emitted 8.3 minutes ago, right? All right, so we step it one further. This is one of the closest stars to us, and it's 4.4 light years away. This is the closest star. So think about looking in the night sky, and there are thousands of stars there. That's the closest one, 4.4 light years away. So if you've got your friend out in Alpha Centauri, and you send your friend a text, it's going to take 4.4 years for them to receive that text. And say they respond to you right away, they're checking their phone constantly, it's going to take you 9 years to hear back from your friend, about 9 years. And I hesitated to mention aliens in this talk, but I think I'm going to right now. That's one of the reasons why, and you'll see the next step, that's one of the reasons why it's going to be so hard to communicate with any possible life out there. Is these distances are incredibly large, and the fastest speed out there is the speed of light. Okay, so that last step here, And this is Andromeda Galaxy, the closest galaxy to us. And there are billions of galaxies out there. The closest galaxy to us is 2.5 million light years away. I don't know. To this day, even after explaining it a number of times, it doesn't sink into me how big the universe really is. All right, so it's really, really big. That's one of the closest galaxies to us. I didn't actually tell you about this image yet, but in this image, you can see a galaxy right here. And you can see the galaxy profile right here. Maybe you can see it's a little bit brighter in here than in this region over here or surrounding. But you can see the galaxy there. You can see a few other stars in this image as well. And I'll tell you, I calculated this out. The distance to this galaxy is 100 times further than Andromeda. It's about over 300 million light years away. And this is, I'll tell you, one of the closer galaxies to us. All right, so the reason why it's so hard to measure distances is that objects are incredibly far from us. But we can do it. We can do it. So, and we're going to do that using type 1a supernovae. That's one of those things. I said type 1a supernovae and magnitudes. So am I able to play it on here? I can maybe my mouse. So this is an example scenario for a type 1a supernova. You've got a white dwarf star over here and a red giant star here. The white dwarf is gaining mass, and then it can no longer remain stable against gravity, and then it explodes. So I want to watch that one more time here. You've got a binary star system. One star here, one star here. It's gaining mass. It reaches its critical mass. It can no longer remain stable against gravity, and then it explodes. All right, my timing wasn't exactly perfect there. All right, so we want to use these type 1a supernovae. It's a specific kind of exploding star for two main reasons. Number one, they're extremely bright. These events are almost as bright as a galaxy by itself. They're extremely bright. And so we are able to observe them super, super far into the universe. So number one, they're super bright. We're able to see them. And they're very consistent in how much light they emit. And this is incredibly important. They're very consistent in how much light they emit. All right? So maybe if you've zoned out a little bit, this is a great time to listen in. This is a hugely important slide in this talk, okay? And it's going to be me describing what it means to be a standard candle, okay? So those type 1a supernovae are extremely consistent in how much light they emit, and that tells you about this principle of a standard candle. The principle being, if you know how bright an object is, if you know how much light an object is, then given how it appears, how bright it appears to you, you can figure out how far away it is. I'll say that one more time. If you know how bright an object is intrinsically, given how bright it appears to you, you can figure out how far away it is. And that's the principle of a standard candle. We are able to take an apparent magnitude, how bright the object appears to be, and compare that to the absolute magnitude, how bright the object intrinsically is, how much light it's emitting at a given distance. And we compare those and are able to figure out how far away these supernovae are. Okay, so I just told you about what a standard candle is, and I have in the top of this slide that type 1a supernovae are standardizable candles. That's what we've understood them to be throughout the course of history. They're standardizable. So what's the difference there? The difference being they're not perfect standard candles. They're not perfectly consistent in how much light they emit. There are a few corrections we have to make to standardize them and have them be more consistent in their actual outputted luminosity or brightness. Okay? So they're not perfect standard candles as we've understood them in history. They're standardizable candles. We have to correct for a few things. All right, so we're ready to measure our distances, right? Our first step, identify the supernova. Identify the supernova. So I practiced my talk with my dad, and we got to this slide, and he said, all right, so we want to identify the supernova. And he said, Erik, I found it. He said, identify a supernova. That's super easy. All you have to do is follow the big green arrow. It's right there. And I said, Dad, oh my gosh. I rolled my eyes, and I said, I put the green arrow there. And of course he knew that. But I will tell you, it's not the most difficult thing. It is difficult, but it's not the most difficult thing for us to be able to identify supernovae. And this is how you do it. I think you'll hear in one of the later talks today, but we are monitoring the whole night sky at all times. At all times. We are scanning always for various objects, many different kinds of objects. And so we're taking images constantly. And so if we're doing that, we're monitoring the night sky all the time, and if something new shows up, we're able to find it. And so that's what we do. We have an image over here from before the supernova has exploded, and we see our galaxy right here. We see the galaxy profile there. And then if we see on the next night, oh my gosh, we see the star has exploded. So we find the supernova. That's the first step. We found the supernova. Next step, calculate the magnitude. Okay? Calculate the magnitude. And we go back to here. Obviously, I'm going to talk about this third panel here. You're taking images every single night and see in the next night, oh my gosh, a supernova is there. And we actually track that over the course of a month. That's the typical time scale for a supernova. It explodes, it gets brighter, and then it gets fainter over the course of about a month. And we watch it that whole time. So what we do is we take this science image and we subtract this template image. And we call that, we difference the images. And we obtain this differenced image here. And so you might expect that, hey, roughly, this galaxy has not changed in the last few days. This galaxy has not changed in the last few days. So if I subtract the two images, then what should be left but only the supernova light by itself? So we look at these differenced images. What you can actually notice, and it's kind of fun, is you can notice a little bit of a remnant right there. Maybe you can see that, a remnant from the galaxy, due to, it's really hard to perfectly subtract these objects. So it's hard to do it at the center of a galaxy. But we difference the images. And what we do now is, so we're left with this image that basically has just the supernova light left there. And we count the light. We literally we count how much light we have received from this supernova. And given how much light we receive, we're able to obtain the magnitude. And we do that by comparing to the brightnesses of known stars. So if you count the light on any given night, maybe you're going to count different amounts if weather, if you have a little bit of clouds or you have a little bit of turbulence. And so you have to calibrate your magnitudes. Calibrate your magnitudes to the brightnesses of known stars. So you know the brightnesses, you know the magnitudes of the stars in this image. And then, if you know those brightnesses, you can compare to the brightness of your supernova in the image. All right, so we've obtained our magnitudes, and now we have the distance. Okay? And maybe that's a little bit of a jump. I'll explain it again, how we get from the magnitude to the distance. We know how bright, roughly, type 1a supernovae are intrinsically. And so given how bright they appear to us, we can compare those brightnesses and measure the distance to us. So now we have the distance. Next up, third step, obtain the redshift. And I said, we need to get the velocity, right? We've got to get the redshift to be able to do this. We've got to get the velocity from the redshift. All right, so back to this picture here. You observe your distant galaxy. It's not actually to scale, but you have your light traveling across space and time and lands on your telescope. And I said this, I hinted at this, but this light has a given wavelength. This light has a given wavelength. It's a wave. And I'll tell you that the light that this galaxy emits is not in just one wavelength. It doesn't just have one. So a wavelength is associated with how much energy that bit of light has. And there are many, many different wavelengths that you receive from your galaxy, across from the longest of wavelengths to the shortest of wavelengths. And that principle, that light has many different wavelengths, is called the electromagnetic spectrum. And maybe you've interpreted or you've experienced light in this way, but light actually varies from the longest and longest of wavelengths up to hundreds of meters long, all the way to the shortest of wavelengths in the gamma rays. So maybe you've experienced or you've listened to the radio sometime. That's actually light information traveling from the radio broadcaster, radio antenna, to your antenna, and transferred to sound in your speakers in your car. You've probably experienced microwaves, near-infrared or infrared goggles, UV rays from the sun, X-rays, gamma rays. All of these, maybe you haven't thought about it this way before, but all of these are forms of light. And just this little itty-bitty sliver is the visible spectrum. And we study, as astronomers, across the complete electromagnetic spectrum. And what I'll tell you is that as light is traveling across the universe, it gets redshifted. It gets redshifted to longer and longer wavelengths. To see this in an image, or a little movie here, as the universe expands, the light itself gets stretched. The light itself gets stretched. And so it gets redder and redder. You can see that on this diagram here. The longer the wavelength, the redder it is. Okay? So as the expansion of the universe is happening, this light itself gets redshifted. And that is what we define, this Z, redshift. It's defined of how much has that light been redshifted. So if this object is a lot closer, it won't have enough time to redshift as much. But the further and further this galaxy is from you, the light has traveled further and further across more and more time and has been redshifted more and more. So this redshift is related to the recession velocity, or how quickly this galaxy is apparently moving away from you, by multiplying by the speed of light. So if you get the redshift, you multiply by the speed of light, and you get your velocity. To describe this in a little bit more complicated scenario here is a spectrum. And a spectrum it was mentioned in the last talk, but I want to go back to our basics here, right? That it's how bright an object is in every single one of those wavelengths. Every single one of those wavelengths. And what we see is this is a spectrum of a star, that it's most bright here in the optical, in the visible regime, and it gets fainter and fainter as a black body spectrum. And what we can see is, and we've tested this and learned about this in labs, is we can see these characteristic dips. And these are called elemental signatures that we are able to use to be able to calculate these redshifts. So if instead of looking at the star right next to us at a redshift of 0.0, if instead we observed this star at a redshift of 0.4, then all of that light will have been moved to redder and redder wavelengths and will have been stretched more and more. And so, given that we know what elements point to each of these elemental signatures, given how much maybe this line has moved from here to here, we're able to calculate the redshift, how quickly the object has moved away from us. So that's what we do. We obtain a spectrum of this galaxy right here. And we can see, we know what the elements, what the spectrum should look like at a given redshift. And so we compare to what we actually receive. And this is what I did right here. There you go, ERP, EP. We know there's these various elemental signatures. Hydrogen right here, oxygen is here, and we see all of these lines. And we know that if we're observing it right next to us, what wavelength, where that line would actually be, and we see, oh, it's been shifted by this amount, and so we assign it a redshift. This is the process of actually doing redshifting. So now we have the velocity. We multiply by the speed of light, and we have the velocity. All right, so now we've measured the expansion of the universe. We have the distance, we have the velocity, we've done it, right? Okay, maybe we need to explain it a little bit further. This concept has already been used for many, many years. It's been used for many, many years. Get the distance, get the velocity, measure the expansion of the universe. And here is an incredibly famous, in my field, figure from Hubble back in 1929. He was one of the first people to provide evidence for the expansion of the universe. What he did is exactly what we've done. He plotted velocity versus distance, and what he found was that for an object, the farther and farther an object is from us, the faster and faster it's moving away. The farther an object is from us, the faster and faster it's moving away. And what he did was he fit a line to his data points, and he measured for the first time what we call now the Hubble constant, a very, very important parameter in my studies. He related the velocities to the distances and figured out how quickly the universe is expanding. Today, this is more like what a Hubble diagram looks like. So that last figure I told you, we call that a Hubble diagram now. This is what a Hubble diagram looks like today. What you have on here, we decided to switch the axes. We've got distance on this axis. That's the distance modulus I showed you a little bit before. Distance on this axis, and redshift on this axis. So it's that same thing. We're measuring distances versus velocities, and we find this expansion of the universe and even this accelerated expansion of the universe. And what we've done is we've plotted here on this plot over 2,000 supernovae. 2,000 supernovae observed in the optical or the visible wavelengths. And then what we do is we compare how well does our data fit to our model for the universe. So we have actually a relatively simple model to the universe right now. It's called lambda CDM. I'd be happy to talk to you more about that afterwards. But lambda CDM, this model right here, fits incredibly well to the data. You subtract the data from the model, and you see it right here. These are the residuals here. The model fits extremely well to the data. And yet, I'm still not quite satisfied. How can we make these expansion measurements better? How can we measure the expansion of the universe even better? I showed you this slide before. I told you we've understood Type 1a supernovae as standard candles. what I'll tell you now is that, and they're standardizable because we have to correct for a few effects due to dust, due to how quickly the supernova fades or stays bright. But I'll tell you that instead of observing in the visible here, this idea that if we instead observe over here in the near infrared, there's the infrared here, but we've got the near infrared, the NIR. If you observe in the near infrared, we've found them to be standard candles, not standardizable, standard candles in the near infrared. So this is a publication that I'm not on, but it has a great title. Type 1a supernovae are excellent standard candles in the near infrared. And this hypothesis has actually been out there, been circulating since about the 2000s. But it's this principle that near infrared light is less affected by dust. Near infrared light is less affected by dust. So here I've got an image, and we're going to compare it to the near infrared next. But here I've got an image of the Horsehead Nebula observed by the Hubble Space Telescope in the optical. Beautiful image, I think. If you observe it in the near infrared, that's what it looks like. There's so much more structure that you're able to see, and it's more beautiful. So in the near infrared, light is less affected by dust. To describe that again, here this is called B68. It's a molecular cloud that we've observed out in the universe, or in our Milky Way nearby. It's a big cloud. It's a big cloud of dust. And if you observe in the optical, the visible, you can't see through it. Okay, but as you get redder and redder, you can see that actually you're able to see through the cloud. And that's because near infrared light can just pass through dust, whereas visible light can't. So near infrared light is less affected by dust. We're able to observe these type 1a supernovae as actual standard candles. I guess I wrote that right again here. So how can we do this better? Let's observe in the near infrared, not the optical, because they are standard candles. So I told you on that previous slide of our current Hubble diagram that the sample of optical type 1a supernovae, the number of supernovae observed in the optical wavelengths, is growing and is more than 2,000 that we use for cosmology. We use for the study of the universe. In the near infrared, there are fewer than 200 type 1a supernovae observed in the near infrared. Fewer than 200. So we proposed, and this is my thesis project, is to add to that sample, to help us out there. We're going to do near-infrared supernova analysis using devils. So I said I'm from Duke. We're the Blue Devils, right? That's what that acronym is. But I will admit I did not come up with this acronym. Somebody from one of my colleagues from Santa Cruz came up with it. So I don't have to be. I wasn't trying that hard. Somebody else was. But it's a little bit of a doozy of an acronym. It's the dark energy H0, the Hubble constant there, and peculiar velocities using infrared light from supernovae, the Devils survey, which makes use of the United Kingdom Infrared Telescope, UCURT, on Mauna Kea. So this is my project. So maybe you were thinking, what's up with that discrepancy? There's 2,000 observed in the optical. There's only 200 in the near infrared. What's up with that discrepancy? I just motivated to you all, we should be observing only in the near infrared, right? No, there's a few reasons why it's difficult. It's difficult to observe in the near infrared. The first being the sky background itself is brighter in the near infrared. So it's harder to actually observe the supernova itself because there's more noise from the sky background. Additionally, galaxies themselves are brighter with respect to the supernova. So if I observe a supernova on top of a galaxy, it's harder to subtract out and be confident that I'm only looking at the supernova light by itself. Type 1a supernovae also peak in the optical. They peak in the optical. They're not as inherently bright in the near-infrared, making it harder and harder to actually do this analysis. And again, we like the visible a little more. It makes more sense to us. We're able to see in the visible. So we've spent a lot more time in history developing and perfecting optical detectors. So there are fewer quality near-infrared detectors out there. So even with all these difficulties, DEVILS is still progressing. We've observed 105 supernovae in the near-infrared. And so I told you that sample is only at 100, or only at about 200 right now that are used for cosmology, and we're adding significantly to that sample. Here I've plotted across the night sky the locations of all the supernovae that I've observed with DEVILS, with my telescope here, UCURT. So as you can tell, I'm incredibly excited about DEVILS, and we're continuing to observe supernovae regularly. So DEVILS is doing great. We decided we want to measure these distances better, and we have. This is one of the final figures in my most recently submitted publication, showing to you that in the near-infrared, type 1a supernovae are extremely consistent in their outputted brightness, in their outputted luminosity. So if you stack all of the observations on top of each other, you can see, especially here, this is the key, that they're remarkably consistent in how they explode and how much light they emit, especially in the near-infrared. If you compare that to what it looks like in the optical, before corrections, this is what it looks like in the optical. There's much more spread in their light curves. But in the near-infrared, they're extremely good standard candles. And we are just getting a ton of good data we're excited about. So, as I close here, now you know how to measure the expansion of the universe. All you need is to get your magnitudes and your redshifts, and you're on your way. I'll tell you, type 1a supernova cosmology in the near-infrared is extremely promising, and it's incredibly important for the Roman Space Telescope, right here. If you haven't heard of the Roman Space Telescope, it's one of the next, it'll be NASA's next flagship mission launching this decade. In my mind, it'll be so much better than JWST. But it's going to observe in the near-infrared. And so we need to, and we think that DEVILS is very important for preparing for the Roman Space Telescope. And with that, DEVILS is just beginning, and we're just hoping to understand the physics of these supernovae so much more deeply. So as I close, I want to just acknowledge all the people that I've worked with and had such a pleasure working with. A lot of these are my colleagues at Duke, and many other locations as well. And here's an image of many of us from that I've listed before, with Duke's Chapel right behind it. So thank you so much for your time and for your listening. I'll take any questions. Yes?
Can you go back to the slide that shows the references to the corrections that are made?
Yeah. Not this one.
It was the one that had the 3 bullet points, I think. And I was wondering what kinds of things are corrected for and that sort of thing. Yeah, that one, yeah.
Yeah, so what you can see here, great question. I'm going to go move to this last one here. So what you can see here, and you need to correct for, is that the faster, so the quicker a supernova fades, the less bright it is intrinsically, the fainter it is intrinsically. If a supernova stays bright for a while, it's actually much brighter. And so we're able to model this. That's one correction we make. Depending on how quickly the supernova fades, that's how bright it is intrinsically. So we model this and correct for that. Another one is the color of the supernova. So given if it's bluer or redder, it has various properties on how actually bright it is. Yeah, up there.
A couple of questions for you. First, I'm familiar with this concept, read up on expansion and redshift. One thing I still sometimes can't get through my head is there seems to be a bit of circular reasoning in what you break it out for. We know what elements, the brightness of elements by their wavelength. We know the redshift by the elements, but if it's redshifted, how do we know that was the original element? How do we know?
Yeah. So I want to repeat what the question, I was supposed to repeat the question from before. We were asking about what corrections do we make to standardize brightnesses for supernovae. And the question now is describing again this how we actually know which lines are which later when we're doing this redshifting. And so it's kind of just knowing the actual shape that it looks like. We've seen enough galaxies, we've seen enough stars that so we know kind of the picture that, hey, this one has 3 bumps, or this one has a super small bump here. We know what it kind of looks like, and we can see that, all right, this is what it actually looks like here at a higher redshift. And so we have a template for what it actually looks like and where it should be originally, and then we can see as it shifts out, it still looks relatively the same, but we can see, we know what this one equates to originally. So maybe you can see, it's just by the shape, the morphology that you have here. So here's a super small bump and then a big bump, right? Over here you see a small bump and then a big bump here. You could tell what redshift you're at given the shape of your spectrum. Yeah, right there.
This may be a physics question, but the space between the galaxies is stretching.
Yep.
Is the space within the galaxy stretching too? And is the space within the stars stretching? And if that's so, is the space within atoms stretching?
So the answer is yes, it is. But on these scales, gravity by itself is able to dominate, and all these other forces are able to dominate over those forces. I believe that someday it will stretch even on these scales, but right now the scales between galaxies are where we can actually see this expansion. Otherwise, within galaxies, we're not seeing that real amount of stretching.
What about the subatomic space? Is that stretching too?
Yeah, so that is a potential explanation for the fate of the universe, is that every single thing separates from itself, subatomically too. Yeah?
Be able to explain the painting of the telescope that you did.
Say it one more time.
Euchre.
About Euchre?
Yes, you didn't provide a background on the name. Oh, its name.
Oh.
I wondered if it had anything to do with my seat. Where I'm seated. Because you follow baseball and stuff.
Where did I? Oh, it's much later. So I was supposed to repeat the question. The last one was about the stretching in the universe. This expansion, is that happening across all scales, inside stars and subatomically as well? And now the question is, tell me more about Euchre. Where is it? It is, so it's on Mauna Kea. It's in Hawaii. I'm really excited. I'm going to get to go there in May. I think, this is an aside, I feel like I chose the best project because now I get to go vacation in Hawaii. But, so this was originally commissioned by the United Kingdom, the Euchre Infrared Telescope. Now it's owned by the University of Hawaii, and it's a 3.8 meter telescope with I think it's pretty big. Yeah. Yeah. Yes, right here.
Easy question and a more
Yeah, great questions. Well, one was an aside, a little aside. So the question asked here was, how often am I observing a supernova? Sometimes it varies. It depends on how much telescope time I have. I'll tell you a little insider information. It's really expensive to be able to get telescope time on these big telescopes. Right now, I can tell you exactly right now, we're following 4 supernovae, but we had paused for a while as I was in the finishing stages of submitting a publication. At any given time, we can be following up to 20 candidates, and sometimes as few as 1. But I'm checking. I should be checking every single day. I'm checking most days for potential candidates as we're monitoring the whole sky. Right here.
How much of it is remote time?
Remote time, I am able to have all of my observations taken remotely. I don't actually have to, I'm not nocturnal. So we have technicians that are nocturnal, and they go in phases. So they carry out the observations for us. Yeah. We have a question right here.
Kind of elephant in the room, so the JWST images that show larger galaxies than they expected earlier time frame.
Yeah.
And follow-up question on calibration, astrometry, to get the Cepheids, et cetera, et cetera.
Yeah.
There's a lot of slop in that.
Oh, yeah. So questions were about earliest galaxies. How's that, from JWST that we've seen, how's that relevant to my work? And then asking me about all the things that I did gloss over in measuring the magnitudes. There's a ton there, and I'm happy to talk to you all about it later. Question up there.
How long is the duration of the life of a supernova?
Yeah.
How long is your observing time on something like that?
Yeah, so how long is the life of a supernova? On scales that I care about, it's about a month long. But there are supernova astronomers who want to look at the light like a year afterwards. That there is still some light there, of course. But what I care about is about on a month time scale in rest frame. Yeah. Right here.
In less than 30 minutes, working with Anna Reese and other people, how is your information narrowing down the tension issue?
Yeah, you're asking about the tension. I don't know if I have a backup slide on that. I think I do. So we're gonna dive in here. Let's see.
You got 30 minutes, so.
No, I don't. Let's see if we can just hunt around here. All kinds of cool things. Hopefully I didn't put anything weird in here. Here we go. So asking about the Hubble tension, figuring out what the Hubble constant actually is, and what we're finding with supernova analyses is that the Hubble constant is up here. And what people are finding is that if you look back to the beginning of the universe, in the early universe, and you propagate out, so you model from what we would expect from the very beginning of the universe, a very precise analysis, they're finding a different value that we should be actually getting for this expansion of the universe. And so repeat the question again. Sorry. I just want to introduce.
How is your information resolving and working towards resolving the issue between the two?
Yeah, so my biggest thing is we want to measure the distances better. And so what my work does is it's going to be just hopefully decreasing the error bars on these measurements. And so in some senses, it'll likely, in ways, because if the error bars shrink, then the discrepancy is that much larger in ways. Some of my other work that I didn't talk about today is in peculiar velocities. Those are measuring, so we have motions due to the expansion of the universe, but these galaxies are also whipping around. And so what I do in other work is I use these models for how the galaxies are moving actually physically to correct for those motions so that we can look at just the expansion of the universe. And that was a comment on, there was a hypothesis that if we correct for those effects, that this tension would move down this way. It actually says, no, it shouldn't actually move down this way. It helps us move back up to this value here. Yeah, right here.
Supernova and cephoids, are there other ways to measure Hubble constant?
Yep. So are there other ways to measure the Hubble constant? Definitely. A lot of people like to put a middle point here due to, instead of using Cepheids, which I didn't talk about at all, their brightness is associated with the way that they fluctuate in brightness is tightly correlated, tightly associated with how far away they are. Instead of using Cepheids, people use tip of the red giant branch. They look at the distribution of stars in a galaxy on a color magnitude diagram, and that can tell you how far away these galaxies are. And they find their result to be a little bit in the middle between us. But we're in the works on saying that their analyses are a little bit sketchy, and so we think it should actually be a little higher. But one last thing I'll say is there are hypotheses, and this is a big debate in my field. There are hypotheses that there's a recent one coming out about early dark energy, saying that there was actually, before we can see potentially, early dark energy that made the universe expand faster than we even expected early on, which would shift these measurements higher up. So there are hypotheses both ways, people trying to poke holes both ways. We're not too mean to each other, I think.